These things are really cool. This was given to me by a company in Utah when I did an Altium user group.
All right.
They hosted it.
We're on the air.
Oh,
You're
we
showing
are.
everybody your thing. Yeah. Hello,
Hi.
everybody. Late, my fault.
Yeah.
Jeez. How's everybody doing? I'm actually sitting here reading the comments from Frank here. He's a lot of good stuff about FPGAs.
Oh yeah, and you mean in the Discord?
Actually, no. It did it do something weird here? Did it?
Well, Frank just posted in the projects channel in our Discord some LED lighting fixture he designed with an
Yeah,
ESP.
no. It just jumped, and I've got last week's comments. So hang on a second.
Oh, okay. So we may not actually be live yet.
We may not be. It says live, but let us look.
I'm not seeing yet on YouTube, but there's normally like a 30-second.
There we go. Yeah, yep. Oh, Jesus. Sorry, everybody, again. We came from behind. We conquered. We got it working in spite of ourselves.
Is that the saying?
Hey, I have a story about Veni Vidi Vici. You mind if I throw it right in?
Go ahead.
So, I used to work with a guy named Terry Ryan a lot, who did the BASIC that's in the Commodore 128 and the Plus 4 series. Okay. And he always left little quips, right? Like when we first got the thing working, the way I knew was my analyzer said, don't take any wooden nickels. He actually loaded the ASCII values and knowing I would see them, right? And he did the message that's in the C128 in the Easter egg that says, link arms, don't make them. So one day we're troubleshooting our asses off, and I'm sitting there, I'm looking at the output. I'm actually on an ASCII analyzer. I'm going, nope, nope, try it again. Nope, what are you doing? Finally he says, what do you get? And I said, just a bunch of V's and stuff. And he goes like this, Veni Vidi Vici? And I go, I guess. Why? What's that mean? It had been working all along. I just didn't speak Latin.
Oh, come on.
So, yeah, so I'm like, just a bunch of V's and I's and E's and things. And so, yes, he had said Veni Vidi Vici in a link. So
that's funny.
Apparently, I've lost a light here in the lab. Hopefully, the lighting looks okay today.
Well, I think you look fine. I am going to say I'm still not seeing the live stream on YouTube. Are you getting that?
I am getting it. Try a refresh.
Did you? Okay.
Yeah, somebody's posted you are live. Yeah.
Okay, cool. I'm not. I guess I'm just on some delay. You know how?
No, the delay's over with.
Yes, we are live. Of course.
Yes.
Excellent.
All right.
Glad to see it. Okay. Sorry. Yep. On with the show.
So that's my Veni Vidi Vici story.
So Veni Vidi Vici, which means I came, I saw, I conquered, right?
I think so. It's been too long. I'm solving too many problems here to actually have good memory.
Yeah.
Is that's what it means? I came, I saw, I conquered.
That's my understanding, but I haven't learnt Latin or that much about ancient Rome. Though I have been to Rome. Have you been there?
No. I've been to Switzerland and Japan. That's pretty much it.
If you or anyone watching or listening ever has a chance to get to Italy and visit Rome, please do. It's a marvelous, beautiful city. Really incredible. And so I've been to, the Forum, the Parthenon. I've visited all the sites of ancient stuff and saw the aqueducts. It's pretty incredible when you consider a lot of that stuff is more than 2,000 years old and still standing. And I always get confused. Is it the Parthenon or the Pantheon? I always get confused. I think it's the Pantheon. But this building that later on it became a church. But in ancient times, it was like a government building, and it has a perfectly spherical roof on the inside.
Right.
And it is really strong. It is made of concrete, and it is the oldest standing concrete structure in the world today. And it is still totally solid and very strong and is not going to go away or crumble anytime soon. And this was made. It's a perfect sort of cube shape, and it has the equivalent of a perfect sphere within the cube on the inside for the domed roof. On the inside of the domed roof,
right.
It has a hole in the middle of the dome roof, which is pretty much a perfect circle to let sunlight in. And this was before they had steel reinforcement. Steel reinforcement in concrete structures is a relatively new invention. So, like, it's just mind-blowing, the engineering that those ancient Romans had. So anyway.
Yeah. Wes is asking, how was the food?
Oh, absolutely wonderful. I can't really eat bread here in America. It just is too sweet for me. And I do occasionally break the rules and have a ciabatta bun with a burger or something like that, or a brioche with a burger once in a while. But I generally avoid bread here in the States because it hurts my stomach, and I'm not even gluten intolerant.
And that's coming from somebody that was raised on Vegemite, right?
Exactly. Bread in Europe, especially in Italy, I ate it the whole time and never had. It was just so beautiful and fresh, and I never had any trouble with it. It didn't hurt my stomach or give me acid reflux, and it wasn't too sweet. The food there, just incredible.
Somebody just asked about the Apollo 68080 Vampire board, which I don't know what the Vampire board is, but I had just watched most of the series from Curious Mark about restoring the Apollo guidance computer. Have you seen any of this?
I've seen some of those, but I think we're talking two different things here. So there's the Apollo.
Yeah, we are. I just used the word Apollo. Yeah.
And that's older and more interesting stuff. That video series is really cool because they're showing like nothing was standardized like it is now. There was no like the power supply alone was crazy. It had some weird voltages, positive and negative, and it's just because it was transistor logic, discrete transistor logic for most of it, right?
Yeah.
So the whole thing was engineered from the ground up before there were standards like TTL.
Right. And in there, they had to do things like they have a core memory. They had they had a broken sense wire at one point, but then they had a broken diode in the potted array that was the sense amplifiers. And so I'm just to the part where they're grinding their way down into the epoxy to fix it and whatnot. And they ultimately, I had seen the last one first. They actually get it all working, running the actual code, and they didn't have the ropes. The core memory was woven as ROM and then folded to go into these little things. They didn't have that, but what they had was what for the day was the flash equivalent of those. They had the ones that could be rewritten, and so they were using rope emulators, but they're still from the original AGC stuff. And the guy did an FPGA so he could act like ground control and write, the controlling mechanism, and fill these rope emulators with the actual code.
Now you know what the beautiful bow on that whole project would be, which I'm sure they're working towards and will do, right, is replay the entire Apollo mission sequence through that computer.
I think I saw them and didn't realize who they were at VCF a couple of years ago.
They could actually reproduce the errors that came up.
Right, the 1201, 1202, yeah,
and actually, basically, wouldn't that be cool? Like,
they do,
so cool.
And so in there they keep running like P63, which is the landing one, I think it was them that I saw at the Computer History Museum, because at one point they're at the museum and I'm going, hey, there's Chris, one of the curators who's no longer with them. So I actually recognized the people, which was cool. And I think they actually do a whole landing and stuff in front of people where they actually hook up a joystick and they have the diskies display and everything and do a whole landing sequence. So it was really cool.
That is very
So,
cool.
and the way they brought it up, they had to bring it up so slowly. They watched it do the reset vector, and then there was nothing on the bus originally, so it jumped to 00, which looked a lot like what we were doing with the 6502 thing that the emulator we saw last week, because the jump instruction happened to be 00. So when it went 000000, it jumped to 00 to start executing. And then one of the first things it gets is an ECC error. And so it keeps restarting. Well, there's ECC because there's no memory, so it's actually doing what it's supposed to. And it was really phenomenal watching them work through. I mean, and the guys were just great. The one guy, he's programming an FPGA to actually simulate the AGC memory then so that they could keep it running and get to the next problem, you know, and it was just a wonderful series.
Yeah, the real hardcore... It just leads me to believe, like, the next step for the real hardcore retro computing fans is to actually wire your own core memory.
Yeah.
Get some 42 gauge.
I have a memory around here somewhere. I haven't seen it.
I got a big reel of that, but it's for making guitar pickups because that's what you use.
No, I actually have a big chunk of memory. I grabbed at VCF one time.
I think that would be a test of your retro computing metal. If you could have the patience to hand reconstruct core memory, because I'm sure there's not a machine left on the planet that can do it anymore.
Jerry Ellsworth did a video on the core memory, the reading and writing back to it and everything. And of course, the thing with core memory is it's read once memory. And so every time you read it, you actually have to cycle back and rewrite it. Yeah.
Talk about refresh.
Yeah.
I'll have to excuse me touching my face today, everyone. I think I got an eyelash in my eye and I can't get it out. So, sorry.
Right.
Bit of a distraction. Yeah.
So, hey, now, did you know about the Apollo 14, that there was a problem on that? That's kind of how I stumbled into the Curious Mark series. By the way, if you go find this series, Curious Mark, M-A-R-C, the abort switch in the LEM was faulty, and it would every now and then signal an abort. And most of the time, the software is not looking for it, but at certain periods in the program, the abort signal would have aborted the actual landing. So they call the guy that you've seen his picture, the long-haired guy from that wrote the LEM navigational software, wake him up at home, and they found that they could punch in. They could do a verb 25, noun something, 401, and that would set this mask bit. And then it would ignore the switch. So they could do that right off the bat. The problem was that bit would get cleared again when they actually did like P63 to start the landing. And so what they did was they ran a different program that said, no, you're already landing. You're already in the mode. So ignore the abort switch for now and go ahead and land even if it comes on. And meanwhile, then that gives them time to re-clear that bit and everything like that. And if they had to abort, they still had a computer by their side that was just for aborting, the main abort computer. So it was all very cool. The guy basically made it so they could land on the moon by having him reprogram the AGC on the fly like that. So that was Apollo 14. I didn't know about that. I knew about the 1201, 1202. I think we all probably do.
And we all know about 13 because of the movie with Tom Hanks, right? And the explosion.
Yeah. Well, I was just reading about the whole bus undervolt V thing on, what was it? Was that Apollo 14 also? The one that got struck by lightning. And the one that got struck by lightning was way scarier than the movie makes it out to be, the series, where they just go, oh, we have a bus undervolt V, cycle the ACR or something. They really did. The voltage was down, and that caused a thing to go offline, and that took all the telemetry with it, and it wasn't till they switched it to auxiliary power that the telemetry came back up that told them, keep going, you're on the right track, you're getting the craft back.
I'll tell you what,
anyways, Apollo week here.
Those guys had huevos rancheros.
Yes.
That took a lot of guts to do what they did.
So what do you have for us today?
Well, first, we're circling back to that. Someone was rebuilding an Apollo workstation as well. Like, these are the two different things that we're talking about. There's the Apollo missions and the Apollo computer, but was there a comment? There was a comment. I was looking for it, but I couldn't quite see it. It's probably scrolled way off by now. So the other thing was the Apollo workstation. That was a 68,000 based 16-bit workstation, and those were actually the original computers used by Mental Graphics when they launched. That's what I read on Wikipedia anyway. And I think there's people out there who've resurrected some of those Apollo workstations as well, that were early workstations that were actually capable of decent graphics.
Right.
Yeah.
Right. Matter of fact, I spent this week, I was trying to find, last time we talked where I did a controller for Cray Semiconductor to manage their CDC drives. I'd forgotten the name CDC. And I used the TMS 320 series of DSPs. I actually used a DSP chip that could do a multiply accumulate.
Point, right? 16-bit fixed point. Yeah.
It does a multiply accumulate in basically a single clock cycle. So it gives an FPGA a run for the money. The only thing is it can only do one thing at a time, where if FPGAs, you can do a whole array of multiply accumulate simultaneously. So I used the DSP to act as a RISC. That's what I did with it.
Yeah, they're pretty capable. There were a lot of those fixed point DSPs from sort of first, second, third generation DSPs were effectively very powerful microcontrollers in their own right, and that whole section of the DSP market has been superseded by ARM Cortex microcontrollers that include floating point units.
Right.
But effectively, all that was missing once the ARM Cortex got to M4, the only thing that was missing that they added between M3 and M4 was single cycle multiply divide and multiply accumulate, and that's where they started encroaching on the fixed point DSP sort of market. But you can still get some good fixed point DSPs, and they're especially popular in audio because there's a lot of well-known, well-established, well-functioning code base out there that people want to reuse. And to rewrite it to work well on an ARM Cortex, you would effectively need to, you'd keep the same C, but you'd effectively do all the same optimization in assembly language. But for the ARM architecture, it'd be a lot of work.
Right.
Yeah, but that's kind of where things went. And so now the DSPs are like ridiculously fast, massively powerful, floating point, pipelined.
Right.
They have to justify their existence, right? So they're all a gigahertz or higher, 32-bit floating point units, and whole, instead of just a multiply accumulate, you have a whole biquad as a lumped element in hardware, or you have a whole FIR of so many taps in hardware. Yeah, they're pretty fast. You've
heard of Asahi Keisai? The old AEG, AKG. So,
sorry, go ahead.
Keisai is. Anyways, I ended up doing a job a couple years ago for Asahi, and I'm thinking the beer, right? And it turns out it's these DSP people, and I know you know who I'm thinking of. I'm just saying it badly.
They make codecs, don't they? They're those.
Yeah,
they were acquired, I think, by TI.
Well, this is still. Gosh,
I
wish
AKN series parts, right?
Right? I can't remember.
Anyway.
I can't remember.
They make chips. It's a semiconductor company, correct?
It's a semiconductor company, and they're well known for their DSP and stuff. They did the DSP of 20 years ago. Yeah. So, well, cool. I'm sitting here looking at your design down in the lower left corner here.
I'm looking at yours. I mean, Who wants to go? I've pretty much finished. I've actually even sent off. Um, I got to trigger happy and couldn't wait to see the boards made, which is dumb. Today was kind of this live stream was kind of going to be another bit of a design review before I go spend money on this. But I'm trying out some new fabs I found too through LinkedIn contacts. So I sent one off anyway just to see how the quality is. Yeah. So this is the final Rev 1 of what I'm now called. So it's funny you mentioned Apollo. The Apollo missions.
Right.
I was listening to a book, an audio book about the man who knew the way to the moon, and it's about the engineer who was shunned basically and ridiculed at first in NASA for his idea of lunar orbit rendezvous, but in the end they had to embrace his plan, and he's the one who did all the engineering and calculations to prove it was the only way that they could do it within the 10-year time frame that Kennedy said. So The Man Who Knew the Way to the Moon, it's a really good book, and that engineer passed away a few years ago, but he just a massive achievement of one tremendously brilliant mathematician, physicist, engineer guy. And he's finally in this book getting the kudos he deserved all his life, but didn't really quite get. So it's funny you should mention all that, because I was thinking, what should I call this thing? The project code name and the name of the PCB file is Jogger, because originally I was thinking I just want a board with CPLD and lots of memory, and I was thinking Jogger not because I'm a runner, but because I was thinking it's something that would jog your memory. It was memory related, right?
Right.
You could remember a lot. Because the idea is to basically make this CPLD SDRAM controller for any microcontroller that can hook up to it by SPI and just have tons of memory at your disposal. And then it grew from there to have a TFT panel and lots of other stuff, serial, flash memory and everything. But I don't like the name Jogger. I wanted to find a name, and perhaps I could do another revision and give the project a better name. If everyone jump on Discord and please give me ideas. I'm all ideas. But for the
are you saying the old name was Jog Your Memory?
Oh, Jogger is the name of the board.
Okay.
But I wanted to give this a product name that has some marketing zing, so people in the open source community might choose to contribute and write software for it and do stuff with it. I want people to use this. But then I was thinking, I was just listening to that audio book, and I was thinking, I wonder what the fuel is, because in the book they mentioned the fuel mixture for launching the lunar module, the LEM, back off the moon to rendezvous with the control module is highly corrosive.
Yes, yeah.
And it automatically
auto-ignites
when you mix it with the oxidizer that goes with it.
Right.
And so I looked it up, and I realized, that I've heard of this before. It's hydrazine. And I'm thinking, because I want this board to launch. I want it to be able to lift projects up and make things possible. So I've just nicknamed it hydrazine for now. And if everyone thinks that's a cool name, so that's the fuel.
I like that. That's
the fuel that launches the LEM. So anyway,
now, I knew
start with that whole Apollo computer story because it ties right in, right?
So I didn't realize it was hydrazine in the Apollo LEM. I watched The Martian and read the book, and in there he creates hydrogen and water from hydrazine.
Yep.
But I thought that the one that they used, I didn't realize that was what was used in where it combusted. There was the one Apollo mission
with a nitrogen compound. I forget the name of the compound, but it's 2 nitrogens and 4 oxygens around it.
Yeah, right.
As the oxidizer, and that stuff. It's almost like nitrous oxide, but a more.
It carries its own oxygen and stuff too.
The big brother of nitrous oxide. Nitrous oxide does the same thing, it's N2O. But this other compound, I forget its name, is N2O4. So
Right.
it's like
Right.
the big brother of nitrous, which people use in their cars or in whipped cream canisters.
There was one Apollo that almost ended in disaster. They had a they had a valve stick open, and they were getting the fumes from the ACS thrusters, and that was highly corrosive. It was
bad. Yeah,
and it got in. Yeah, they had like problems talking and breathing and stuff until they got the smoke cleared out of the cabin. Yeah, you don't want to have a smoke-filled cabin on reentry, and that's essentially what they had with their own blaster thruster fumes coming in. So, hey,
Yeah.
you mentioned jog your memory since I'm in the. Oh, by the way, before I forget, I will be appearing at VCF West this August. Virtually, and we'll be talking about the new book coming out. And then we just finalized, I will be appearing at VCF East in person in October this year. Bill Mensch will be following me, so I get to introduce Bill Mensch to everybody. So everybody be thinking about both VCFs.
So we're going to be posting links and any kind of...
all the I lost you there, but we'll post all the information regarding that. So, while Ben's gone, I'll tell another story then. You there, Ben? Nope, we're losing you. So, you're back. You're back.
Sorry.
Hey, I was going to tell another quick story, so let me spit. Yeah, I'll spit this story out. You mentioned you just happened to have used jog your memory earlier.
Yeah.
After Commodore, I ended up at doing some work with some of the ex-Commodore people, and Yash Terakura, one of the people behind the C64, which you may have heard of, had done a sidecar for a tennis shoe. This hung off the back of a tennis shoe, had a G sensor in it. We worked with the bioengineering department of the University of Pennsylvania, and we found that the length of time between strides related to the length of stride and everything. And they coupled it with Adidas and a memory card that goes in the old PC architecture. It was a memory expander, or there was two kinds of ways to expand memory. Expander was one of them.
Yeah,
and so
expanded and extended.
Extended, right. So this was an expander. Right. This was an expander. It used the window into memory as opposed to adding more memory. And so that combined with the cable and the tennis shoes was called Jog Your Memory, and it was Adidas. So they actually, you happen to mention marketing fluff. That was marketing fluff from the 1980s.
Yeah.
And then one day I'm watching Adafruit, and on Adafruit they show one of the tennis shoes, and I'm like, oh my God, the first wearable, and it's from the 80s, and I know the guy that did it.
Amazing.
So,
yeah, someone
I'm
was
sorry.
suggesting Juggernaut. Mike's saying the lightning strike was in '69, November '69. Yeah. Anyway.
So somebody's asking about Jay Miner. I think Jay Miner's dead, isn't he? No, I didn't know Jay. I knew of his dog, and I mentioned that to somebody, and they were like, "Would you stop talking about Jay Miner's dog? Oh my God, I hated that dog." His dog's name was Mitzi. And they actually put her paw print inside an Amiga or something like that.
That's funny. Mitzi, not Misty. I had a dog named Misty years ago.
Yeah. This programmer, she's like, it smelled in it. It was always scratching itself and everything. So that's my one Jay Miner story.
Dogs
Sorry.
do that stuff. Dogs
Well,
are always...
But you get the idea. It was always around the office, and it was like, yeah. So
real
hey,
quick, let me
before you jump into your...
Yep.
Go ahead.
Go. No, you go.
Well, I was going to ask, what PCB firm did you end up trying to plant this with?
I actually put orders in two, which is a bit jumping the gun. I put an order in PCB Way because I've worked with them before, and I know Simon there, and we'll probably try and do something with them on this show and do a sponsorship or something.
I was thinking about that this week. Yeah, getting hold of Anson Bauer or somebody.
They come back with any ideas that seem good, but the other one, which is a new one that I tried that I've never used before, and it was just through a LinkedIn connection I heard about them, called Next PCB. I've already given them some constructive feedback let's say, about their website and the ordering process, because it wasn't perfectly smooth and there were a few confusing things about it. But overall, like what I've noticed about the Chinese fabs that do low-cost prototyping, so PCBWay, Seed Fusion,
JLPCB,
JLC PCB, Next PCB, and even others I've looked at since then, they all have the exact same quoting web page. I don't know if you've noticed that, but pretty much they either all just copied each other, or it was one company that wrote the software and they all just used the same software.
Right.
One thing that I did appreciate about Next PCB is they wrote a cross-platform DFM checking tool for their fab. That's a free download, so you can load any Gerber files into this, and it's a viewer, but it also does full DFM checking. So if you needed an additional, like for any other process, tools like Altium come with something built in that's called Camtastic. I think Mentor Graphics has something kind of built in that's a cut down version of Valor. But if you're using Fusion like me or Eagle, or if you're using other tools that don't come with a CAM editor or any kind of DFM
Sierra
checking,
or somebody,
we have DFM checking, but it's built into the DRC and the PCB design. So you can do most of the checks you need, but if you want to actually visually check and do extended DFM checking around etching tolerances and things like that are very much focused on fabrication, this Next PCB download is actually not bad. It's based on Qt, so I'm pretty sure it's cross-platform. I could probably open it up. I haven't really learned how to use it yet, but let's see if I can find it real quick. Let's see. It should be...
Isn't it Sierra that also has a pretty good online DFM tool, if I remember right?
Right. A lot of the... Pretty much all the American fabricators have one on their website that's kind of built in.
And the overseas ones, a good overseas one will give you an email saying, "Hey, did you mean to have this trace just floating in the air?" They still, a lot of them have somebody that glances at it for you. Yeah. So my only problem with PCBWay is they don't have a cheap controlled impedance product.
I don't think any fab does.
JLC PCB does.
Really?
Yeah, absolutely. I've actually talked. Yes, I have. And that's so is Mike Fikes. It's not controlled impedance. It's controlled dielectric. But if you know the dielectric, and it skips that whole where they paste it up and make sure that it does what you need it to do step. And it's like going to Osh Park and getting FR408. Well, it's a controlled impedance, so controlled dielectric, so you can calculate the impedance from there. At JLC, I'm trying to remember what it's like a Rogers material. It's like a 4003 type analog. I'm sorry, I use 2313, so that at 50 ohms I get about a 6 mil trace. Otherwise, with their other product, you end up running a much wider trace to get 50 ohms. So when I did that when I did the testing on PCBWay, I was actually able to experience the artifacts of the weave in two directions were dissimilar. So basically I've shown that PCBWay is great for the cheap stuff, but for controlled impedance, I end up on JLC PCB. I hope that opinion doesn't mean we can never be our sponsor, but and I spoke with them about it, and they gave me a credit to order a board, and I'm like, no, you're missing the point. Is I want to do controlled impedance, but without. Mike just posted JLC 2313.
It may also depend on what materials they stock in the factory. See.
Well, they started with a better material.
Yeah. So if they've somehow found a supply of a generic copy of
right.
Material,
That's why I called it an analog.
It's very easy for them to do that. but maybe it may be that PCBWay is using genuine Nelco material.
I thought it was the opposite. I couldn't find them using any.
Oh, well.
So you can get Rogers from PCBWay, but it instead of being $40 for a set of boards, it was $400 because they still did that cycle of impedance checking and whatnot. They didn't allow you to do a full online order for impedance controlled on PCBWay. You still got into that reiterative thing like we do in America.
Yeah, this is
all right. Your screen just went black.
Well, this application is not. It's not refreshing the display adequately. I think it might. It doesn't appear to be very compatible with different screen DPI settings either.
Right. But Frank Bus just verified. He said when if you specify a 10 centimeter by centimeter board, suddenly the price jumps up to $290. And that was my experience. It jumped into the hundreds of dollars for what you can get from JLC PCB for $90.
Okay, so this is
90.
kind of working now.
All right. Let me expand it here.
This is a pretty good cam preview. So it's probably, I'd say it's a step above just a Gerber viewer, because there's plenty of free Gerber viewers out there you can download from pretty much anywhere. There's even lots of online ones on websites.
And Altium has one built in, yeah.
Well, almost every tool has at least a viewer.
Right.
This one is from the manufacturer, but it has impedance calculation. I haven't tried any of this, so I can't vouch for its accuracy. This is brand new to me. I downloaded it last night. So copper area. So there's a few calculators built in. How much utilization, solder pad, all sorts of things, object snapping. And obviously you can turn different layers on and off. You can make them visible or invisible by clicking these obscure little icons here. And it's got the additive coloring. So here I've got my top solder mask, top silk screen overlaid with the bottom layer, which you wouldn't normally do really. What I want to do is look at my bottom layer and the next layer in, which is the ground plane under the bottom layer. And we can see the overlap there. And you can see I did do some routing on that layer, by the way, for the FPGA core voltage, which is part of the design review I wanted to do today really quick, is sort of go through the power supply scheme and ask you some questions too, because you've done boards with ESP32 on them, and this one also has ESP32, but plus an FPGA, and they're lashed up together. They've got lots of signal lines going between them, and then you have to start thinking about power sequencing and power up and all that. But the FPGA, there's a variant of this FPGA that has a 1.2 volts core voltage. So I decided to separate the power supply with a 3 volt or 1.2 volt linear regulator variation, depending on which FPGA I put on the board. If it's the 1.2 volt variant, I can switch the regulator out for a 1.2 volt regulator. And then these, on this plane, it's all ground plane except for these lines here that provide the 1.2 volt core to the core voltage pins. There's one on each corner of the chip. And for the most part, the ground plane, which is red or white under the bottom layer here, is unbroken under the signal nets. So I think I've done a pretty good job. These ones here cross the splits in the plane, but these are not high-speed nets or radiating nets. They're not clocks or anything like that. They're like driving an LED or so.
How many layers is this?
This is a 4-layer PCB. So here's my bottom layer. This is the bottom layer.
Right.
Let's zoom out. What's the zoom control here? I guess that's to zoom. This is the bottom layer. It's mostly VCC, 3.3 volt, which is also I/O voltage of the FPGA, plus some signals. And then if I go to the next layer up, turn this one off. This is the bottommost ground plane. Some 5-volt rails and the 1.2-volt rails. And
so you are splitting your ground plane, though, a little bit.
Yes, but no signals, no other signals are crossing these on the adjacent layer.
Okay.
So I've been careful to avoid signals crossing these splits. And then this one is this is the upper ground layer. And again, I did end up routing some low-speed non-critical nets through there. And a 5-volt link there. But apart from that, it's unbroken ground. And then this is the top layer. And if I include both of these, there should be different colors when I select them both. You'll see that I am running some signals here. These signals go over to the rotary encoder, which is on the other side of the board. So they're not high speed. And the rotary encoder also has RC networks on the switch contacts to help debounce it, but also slow down the signal transitions. So
can you show just the ground plane and the VCC plane?
Yeah. Mind you, they don't have a lot.
See how they crisscross each other? You know, so if I go totally by the book, I'd say go to 6 layers.
Wait, these are both grounds. They're actually both grounds, and they're far apart in a 4-layer stack up. They have the core between them, so they're 1.1 millimeters apart. So there's very little capacitance, but these are both ground. That's why.
Why not make a ground plane that's completely unsplit, and then put both of these kind of signals onto a different ground plane?
That's exactly what I did.
You have.
But what you just said is exactly what I'm showing you. These are both ground planes. One's upper, one's lower, but they're both ground. And the lower one, I'm also transferring a little bit of power supply on. But the signals on the bottom layer, which are right next to that ground plane, don't cross any of those splits. Does that make sense?
It does.
I'll show you the bottom layer with it. Here's the bottom layer, and I'll turn that one off. So this is the green is the bottom ground. And adjacent to that is the bottom layer where the signals go. And you'll see the higher speed signals, like the SD-RAM. This is all SD-RAM up here. So all the SD-RAM signals come out of that side of the FPGA and they go straight over here. They're not crossing any splits. And I have stitching vias as well around them. Plus, I have the SD card, which is way down here, and all the SD card signals, which are SPI, they may go up in the tens of megahertz, sort of clock rates and things. I'm not really sure yet, but it's tens of megahertz. So we want to at least have not radiation, right, from EMI. So those don't cross any ground splits. They all just go straight up there. And then links between the ESP32 on its SPI bus and other signals from the ESP32, that's here. They all just go straight up to this side of the FPGA, and they don't cross any splits. And then from the JTAG signals from the FTDI USB JTAG chip, that's a FT2232, that's down here. Those signals go straight up there to that side of the FPGA and also do not cross any ground splits. Does that make sense?
It does, but if you're looking at the power usage of your chips, and forget the signals for a second,
yep.
My question is, if something on the right needs power and the power source is on the left, then the current, the actual ground current, will have to flow around the split you've made.
Yeah.
You know, forget the impedance control for a moment. You can't get ground left to right without going north and south.
The power is... That's right. The power is the other side of that loop. So that's why the power plane basically has 0 splits in this area where the SD-RAM and the SD card and the DRAMs connect into the FPGA. Yes, there are some splits here, but I kind of feel that with the decoupling spread around the chip as it is on the top surface, I probably have enough of a pool of energy there to satisfy any requirements the SDRAM chips would have. The SDRAMs, of course, have tons of decoupling caps. So if we look at the top layer, we can see all these decoupling caps for every power pin on the SDRAM chips. There's a decoupling cap, and also all the I/O bank power pins on the FPGA have their local decoupling caps and punch
What's
down
your clock
straight
speeds?
The master clock into the FPGA is 50 megahertz, but the clock for SDRAMs is probably going to be 100.
Right, and so some pretty fast rise times. Yeah.
So this was something I wanted to ask you about. So I've got two chips that these SDRAMs according to their data sheet and speed grade can go 160 megahertz SDRAM clock. I'm going to underclock them because the FPGAs I'm using probably won't be able to go that fast. Even though it's rated to 172, like you'd have to have a perfect place and route to get full performance. You know how FPGAs are really. So these will probably be at about 100 megahertz. But each chip is sharing the address and data lines and byte selects. The only thing different is chip select. And so with that in mind, I'm slowing down my memory bandwidth by, I'm cutting it in half because I'm only going to chip select one part at a time.
Right.
But I think for the target application, which is driving a moderate TFT panel, which could be driven directly from a microcontroller if you really wanted to, but with some more better performance for 2D animation, say. I think it will be perfectly adequate speed. And
can you show just the VCC rails?
I can.
Maybe on the actual application, because I want to check the position of decoupling caps and I treat power lines. I treat power lines as if they're signal lines.
Well,
and so I don't like stubs, things like that. I like to grid the power so that it doesn't run like an inch and then feeds an FPGA. I like the power to keep going by the FPGA and reconnect to VCC somewhere else or be on its own plane.
I treat power and ground like this big energy lake. And normally I would like to have close planes that are unbroken, but I'm trying to make this board 4 layers because I don't have parts on both sides and I'm not using BGAs. So I wanted to keep it simple. And I also want to make it affordable because this is an open source project. I want anyone to be able to build one and have an easy time with the cost of a 4-layer board. But I've still done it the best I can to reduce EMI. So, but yeah, if I go to, here's my 5 volt, right? So you can see the 5 volt there comes in from the DC jack. There's a diode. I know I've got some drops across the diode, but the whole system runs on 3.3, so I don't care about a diode drop on the input. Also from the USB connector, there's an input from the diode through a diode. It's a simple diode auctioning of 5 volt supply, decoupling cap, and then into a little switching regulator. Also
Can you zoom in?
Volt. Yep. Also 5 volt. That's too far, sorry. Also 5 volt comes in. This is a switching regulator that gives us 3.3. Probably can't see my crosshair mouse cursor there, but that 5 volt also goes to the switching regulator that's a boost converter for the TFT backlight because that needs like 24 volts because all the LEDs are in series in the LCD panel for the backlight. So that's the boost converter that's recommended by the manufacturer of the LCD, and they sell the chip. I bought the chips to go with it. And so that goes off to the LED anode and cathode there. And then 5 volts also comes over here to the core regulator, which depending on the variant. So I've got two design variants here. One, so I'll come back to that. I already mentioned that before, but this is the regulator for the FPGA core, not the I/O. The I/O is powered by the main 3.3 volt rail, along with everything else. And the 5 volt also goes over here to the rotary encoder. And the only reason I bothered running 5 volts to that was because it has an RGB LED in the shaft of the encoder. And blue LEDs typically need 3.4 to 3.7 volts. So you can't always run them off a 3.3 volt rail. And so I decided to run 5 volts over there to drive the LEDs, and that meant I needed a 74HC125 to do level shifting to drive the LEDs from the outputs of the 125 buffers.
So what's your trace width on the power lead going to the PGA, for example?
This one over here, this trace is 30 mils wide. The main input trace is 50 mils wide. So a 30 mil trace, and it's...
Yeah, that's... Okay, it looks smaller.
It's 30 mils. It's not going to have... These FPGAs, these Mark X02s, one of the reasons they're really nice is they don't need a lot of power. They don't pull super heavy current for the core. The I/Os might, but the I/Os are being powered by this switching regulator down here, which can provide a couple of amps. But the core, it's a 1 amp regulator, but so let's have a look at that. So here's my 3.3 volt, and that zooms out and highlights almost everything because of the plane connection. But this is where 3.3 volts comes out of the switching regulator and goes straight down to the bottom layer, which is the whole bottom layer. All the polygon fill on the bottom layer is 3.3 volts. So I've got a 3.3 volt, wherever there's no routing on it, it's 3.3 volt coupled to the immediate ground plane above it. And so I get some decent capacitance there, even though that's broken up by signals going to the FPGA on the bottom layer. All around, I've got my 3.3 volt connections from that plane, that polygon on the bottom layer, through to the I/O pins, the 3.3 volt I/O pins all around the FPGA, and punch down with vias and decoupling caps right next to the pins wherever I can. So I believe that should work pretty good. What else? I did run a 3.3 volt around here because I was concerned if I go to my bottom layer, which is the 3.3 volt layer plus signals, I was concerned that my 3.3 volt, let's zoom out a bit. I was concerned that my 3.3 volt was getting pinched off down here by all these signal traces. And so that the only way for 3.3 volts to get to my audio circuit, which is all clustered on the right, was going to be past all of the FPGA and all around the side of the board, around past these SD-RAMs. And then down here, I was worried even my 3.3 volt plane here might become a bit noisy in this audio section, which I really don't want. So I ran another... In the next plane layer above, I chose to run another 30 mil trace, or maybe I think it's a 30 mil trace from here over to here to help power the ESP32 without forcing current to go all the way around the edge of the board. It's going to come more directly along the bottom here, and so as to hopefully not interfere too much with my power supply to the audio codec, which is to the right. So does that make sense? Or am I...
It does. I've done that. Where I actually draw the connection I want. If nothing else, it's a good visual aid for how copper should, make a bus bar type thing.
Yeah.
What's the cost difference between this and a 6-layer board? This almost screams out to be a 6-layer board, I'm thinking.
Yeah, I'll see how it performs with 4. The
Yeah.
cost difference is pretty big. If you add 2 more layers, that's another whole lamination cycle. So you're almost doubling the cost of the board. Now the board's not too bad as a 4-layer board. Next PCB, I'm getting 5 of these, and it's a pretty large board. If it were under 100 by 100, it would be significantly cheaper. In fact, as a new customer, they would do 5 4-layer boards, 100 by 100 for free, and just charge shipping. They have a deal. But
Right.
because it's more than 100, it's 143 millimeters long and 74 millimeters high. So because it's outside that 100 by 100, it's costing me more. It's going to be
Oh, lost you.
I went away. Am I back
Yep,
yet?
you're back. Yes, you're back.
Okay. Five boards, quick turn prototype from Next PCB with shipping. 4 layers is $90. So it's not bad.
The I'll tell you,
The 6-layer board would be about
price
double.
price that out on JLC PCB would be my advice. As you know, both 4 and 6-layer. After the pandemic, I felt like PCBWay's price jumped up and never came down, and so I was getting differences of $20 on JLC and $60, $70 on PCBWay.
Yeah. So again, if I could shrink this whole thing down, but I didn't. I wanted it to be the appropriate size to have this decent sized LCD panel on the back. So it's like a 5-inch LCD panel. So it's not small. Plus room for a rotary encoder on the side.
You got me curious here. So you said 140 millimeter by 70?
By 143 by 74. So
All right. For a 6-layer version of that on JLC PCB, it's $135. For how many? For 5?
5.
And for 4 layers is...
That's about $40 more.
And for
So
4 layers,
it's like 50%. 50%.
It's $39 for a 4-layer board from JLC PCB.
For this size?
Yes. That's what I'm saying. It's cheaper on JLC than PCBWay.
Is that including shipping cost? I'm including shipping costs in my quote. This board, a run of 5.
I wasn't including shipping. Okay, that's the problem we're having. Then,
so this board, I'll tell you, without shipping, this board, a run of 5,
right,
from Next PCB, 4 layers, was like $23.
There you go. That's okay. The problem was the shipping. I'm going, that's not their prices. Their prices
Well, I like to include the shipping in the quote because
that's fine. Yeah.
That shipping cost is so expensive that's where they can fudge things in, and if you buy something off someone on eBay or Reverb or whatever, they'll say this is the price plus, and they'll give a fixed quote for shipping, $60 shipping. Well, the shipping may end up only actually costing them $13. So they've just that's where their extra margin is.
Well, that's why I call it shipping and handling sometimes.
It
got handled.
Handling charge. Right?
Handled, yeah.
Yeah. So
when will you get these boards in?
I don't know how long they'll take, probably 2 weeks. Obviously, when I get them, we'll take a look at them and we'll examine the quality.
And how are you going to assemble them? Are you going to
I'm getting
solder
stencil too, by the way. The stencil's just another $10 on top.
Right.
So I'm gonna stencil them and hand place and use my oven, which I'm not looking forward to that. It's better than hand soldering, though.
Well, that's why I was
Just the
wondering.
placement, it's going to take a while because there's a lot of
I
parts.
have hand soldered TQFP 144s and gotten away with it. You need a nice chisel point and you just draw the solder down the leads. But an oven's better.
Yeah,
You're back.
not looking forward to the placement. Not looking forward to the placement process.
Right.
Yeah, Dan's type.
Well, that's
Dan
why I
is
taught my son how to do it. And my son's an excellent placer and solderer now. So he's got the ability to sit down and concentrate, whereas I kind of don't,
Yeah, and what I plan to do, because I'll have 5 boards, I'm only going to partially assemble the first one.
Right. Now,
because I want to just get part of it working and test that and make sure that things don't blow up or that I haven't made some fundamental error first. And then,
I always measure ground to +5 or ground to 3 volts before I stuff the board, just to make sure I've got a board that's not trash.
I'm going to I'll do the essential open short test. And then, so a couple other questions I wanted to ask you about this. So I know we're probably running out of time. We've already been going.
Yeah, we're over. Yeah.
So I'm running the ESP32 off the same 3.3 volt supply as the FPGA, and they'll both come up at the same time. And now, in my experience in the past, I've done a lot of other FPGA designs. When they first power on, all the pins are in a high impedance state. So typically, they're designed to do that for this very reason. And then once the program has initialized, which with a Mark XO device, they're pretty much instant on, almost instant on, because they have internal flash. But by then, the ESP also has its pins in a high impedance state, and then it will be configuring its I/O as either not configured because I haven't programmed it yet. So my concern was not blowing something up before I've written any code. But yeah.
All right.
The TFT, I'll put the connectors on. They just use ribbon connectors, so I can put those on and test everything else before I actually connect the LC display.
Right. And tell us again what this product does when it's finished. What is it?
It's a general purpose compute board. It has an ESP32D module. So it's got Wi-Fi, Bluetooth, dual core Tensilica processors, which have some DSP instructions, and high-speed serial I/O. The USB, the FT2232 has one side configured as a serial port that goes straight to the ESP32. So you'll have your ESP32 with its auto configuration on reset capability, or from the FTDI chip. So you can use the normal toolchain to develop ESP32 software for it, and the rest of its IOs, apart from the audio connection, goes straight to the codec from the ESP32. So we have I2S bus codec IO for audio, and all of the rest of the pins are connected straight to the FPGA. The FPGA is blank, of course, and will have to have a hardware program, but it's going to have an SD-RAM controller that gives tons of SD-RAM to whatever devices its master. It also will have the TFT controller, so it will be configured to use the pockets of the SD-RAM for double buffering and video output to the TFT. It has the touchscreen controller going to it. It has a rotary encoder going to it. So basically everything else connects to the FPGA in the middle of the board, including the FTDI. The first channel of the FTDI chip is JTAG, and that's going to the FPGA for programming and debugging the FPGA as well. So, and I've also broken out the JTAG pins of the ESP32. So if you wanted, but those also connect into the CPLD or the FPGA. So you could leave those pins unprogrammed on the FPGA. They'll be floating, and then you could use a separate JTAG adapter to do JTAG debug on the ESP if
Right.
you wanted to.
Right.
Or you
Right.
could do it through the FPGA. You could my intention was once the FPGA is running, I can update the FPGA bitware to connect the FTDI JTAG pins from the FPGA through to the ESP on the other side. And so
Right.
I'll use it to debug the FPGA first, and then once that's all done, I'll update it, and it can then be debugged for the ESP.
So we did get a comment from Frank Buss saying he may have witnessed spikes of 500 milliamps on the ESP32.
Yeah, probably if it's looking for something, yeah.
Or
That's a good
power
point.
up. Yeah. So check your bulk capacitance again, since you don't have a VCC plane.
That's good advice, Brent. You've got 100 microfarad. I actually have. Let's look at the power supply real quick there. I have two 47s, so I have about 100 plus whatever else is hanging off. There's a lot of decoupling hanging off the 3.3 volt supplies as well. So hopefully I've got enough. I guess we'll find out, huh?
Yeah, you are going to, yeah.
Because I'm also pulling LED backlight. That's going to pull quite a bit of current from the 5 volt supply. Because it's stepping up to 24 volts at 20 milliamps. So that's, you do the math in inverse of that. That's a fair amount of current from 5 volts. And then the VCC core doesn't pull a ton of current. But so in here, I've got this. This is the nice thing about these SOT223 regulators is there's a 3.3 volt one in there now. Because the parts I bought are the 3.3 volt core variants, but I designed it so that if I go to, document variant, I have a bill of materials variant for a HEZ lattice part, which has a 1.2 volt core voltage. And in that instance, these part numbers for the actual lattice part number changes to an HE instead of HC. And then I also have, I haven't finished doing this yet, but this part U10 will change its part number as well to be FAN 1112, which is the exact same pin out. It's just drop it in the same spot. And you get 1.2 volts output instead of 3.3. So
now, typically when I do the little powers, like you get that. There you go. Typically, I decouple right in front of that power regulator also.
Yes, I would normally add one there. I'm considering that I already have these. I may end up adding more. Actually, that's probably not a bad idea. I should do that on the 5 volt rail. Add some lower value ceramic.
If you got the room, they don't hurt. Yeah.
I do have the room for that, actually, so I should probably do that. So that's a good tip. Other than that, this is just basic stuff. I've got my SD RAM chips. They're, as I mentioned, they all share the address and control and data buses. The only thing they don't share is their chip select. So I'm purely... Yes, I'll be running these at lower speed than what they're capable of, and even at half of that again, but I think that won't be a problem for the intended use of this design.
Do you have a good memory test that pounds the memory?
No, I should probably do one. I should probably find one. Or find one in software so the ESP32 can run a memory check through the FPGA. Because I've bought the first memory chips I bought for this are cheap. I just bought them off AliExpress. Who knows how good they are?
Well, that's how we detected noise in the old days. Is something would give the appearance of working, right? But when you pounded it, then you really found out if it is working or not, because suddenly now statistics are working for you than against you. I've seen systems that I've seen computers that actually don't work in real life, but they appear to work, right? They work statistically well enough that if the Commodore 64 comes to mind, the mean time before that thing fails was 20 minutes. And we could prove that with a good memory test, where we said, oh, look, the memory's always broken. That's why it makes it all the way to 20 minutes before it breaks, though, in a noticeable way. So, yeah, I'm a big believer in pounded memory test.
So somehow all the games I played as a kid
That's right.
didn't get to that memory location. It was a problem.
We had the customers knew that if it locked up to just power cycle it and start again. And I had somebody call me and say, I'm running my business on a Commodore 64, and I'm like, why would you do that? Right? Because it was a game machine, first off,
Yeah, but you could. I mean, there weren't a lot of other applications for it, but it was a good computer.
Yeah. Right.
So this one, I know it's a little bit different, and it probably cost-wise would cost more than a Raspberry Pi if it was made en masse. But you know what? It'll be completely open source, and I'm kind of hoping Frank, maybe Mike, and some of our community members will once I've done the hardware prototyping and we've debugged it, could actually help us write some software for it to do some cool stuff.
Yep.
That's what I'm hoping.
Absolutely.
I know everyone's busy, but electronics is about passion, man. You gotta.
No argument there.
Cool.
So we're 15 minutes past the hour.
I know. So we're out of time.
Nope. It'll have to wait. Yeah, there's a. Oh wait, let me just click into it.
Week? Can we do this next week?
There's the 6502 core. Yeah.
I love it. So this is in an Altera device?
Yeah, this is actually that little 6502 board thing that I was working on before I parked it
before
the pandemic.
You're saying it's a Max series, it's a CPLD or crossover CPLD?
No, this is a Cyclone 4.
Ah, Cyclone. So it's a pretty...
No, I'm sorry. Cyclone 10. I got that wrong the day that I was talking about...
Yeah.
Yes. Yeah, the day I was talking about these little guys. That's a Cyclone 10 on there.
Yeah. Cyclone 10, not a Max 10.
No, Cyclone 10. Though I do have a Max 10 thing here too. So
yeah.
All right. Well, hey, we should get going here. It's 15 after. We'll try and show some Altera stuff next week. But that's good if we run out of time. That means we had a lot to talk about.
There's always a lot to talk about. This is some days we're
I have books to show,
We're feeling burnt out from a whole week, and Fridays, it's the end of the week, but yeah.
Well, I forgot what time we start on Fridays. I missed a Thursday meeting, so I'm sitting there waiting for 2:30 today Eastern, because that's what time my Thursday's meeting is.
I see.
Yeah, so I'm totally a burnout. Guilty.
Hey, we got it done. It was good. Thanks, Bill.
Yes. All right. Thanks, Ben, my friend. We'll see you